Okay, let me know when you're
Yes.
like ready to start. Start now?
Yes.
Okay. So good morning or afternoon, or whatever time zone it is for you. And welcome back to the IEEE ComSoC's TCC and SIG on AI and machine learning in securities virtual seminar series. That's a huge mouthful. We've been doing this, I think, almost as a response to the pandemic, and the response to the seminar series has been really good. I am the chair of the ComSoC SIG on AI and ML security. My name is Subhalakshmi. I'm a professor at Stevens Institute of Technology, and vice chair is Professor Dola Saha from University at Albany, SUNY. So,
Subha, just to pause you, that we are not seeing the slideshow.
You cannot. I know. I decided to leave it here because it takes over my entire screen. And
okay, that's fine.
Yeah, but you can see the slides, yes?
Yes.
Okay. So just a quick introduction to AI/ML-Sec. We are a special interest group within TCCN, and we started from like 15 to 20 members. Now we are over 400 members. You can find us at LinkedIn. Here, this link gives you quick access to the LinkedIn group, and it's also searchable under the name of IEEE AI and ML and Security Special Interest Group. Or you can just email either of us, myself or Dola. So as I mentioned, this virtual seminar series started in November 2020 with Professor Winspoor from Princeton giving the inaugural lecture. And since then, we've had 13 speakers. And our next speaker is Dr. Arup Bhuyan. I will introduce him in a minute, but before that, a couple of logistics. You can view the recorded talks on YouTube channel. The link is here. The entire slide deck will also be available at the the SIG website will also give you more information about the talks and the people that have given talks. Everybody is muted upon entry, and you will stay muted throughout the talk, but that doesn't mean that you shouldn't be asking questions, especially with technical talks. It's difficult to remember how many questions you have had about what the speaker is talking about. So just feel free to keep typing your questions in the chat box. At the end of the talk, we will read out the questions, and then the speaker will answer. So today's speaker is Dr. Arup Bhuyan. He is the technical director of the Wireless Security Institute at Idaho National Laboratory. The focus of his research is on secure implementation of future generations of wireless communications with scientific exploration and engineering innovations across the fields of wireless technology, cybersecurity, and computational science. So specifically, he is trying to lead and focus wireless security research efforts for 5G and beyond. And he's focusing on national impact and secure communications for nationwide unmanned aerial system and for 5G spectrum sharing within distributed scheduling. So Dr. Arup has extensive industry experience in wireless communications from his work before he joined INL in 2015. He received his PhD from Yale, and he's a senior member of the IEEE. So at this point, I will stop sharing, and I will open the floor up to Dr. Bhuyan.
Thank you for the kind introduction, and let me share my screen and let me put in the slide mode and move some of the windows around here. Let's see. Can you see it all right? Let me make sure I see some other stuff around here.
We see it fine.
Okay. All right, just I think I'll then proceed. I don't see the chat screen anymore, but I think due to as you explained, we'll look at it at the end for any
Yeah, don't worry
questions.
about the chat now, and let nothing distract you. Go ahead with the talk, and then we'll do that at the end.
Okay, thank you so much. And it is my pleasure to be here to talk about 5G, its security and use of AI/ML to enhance it. My name is Arup Bhuyan, and I'm with the Wireless Security Institute at Idaho National Laboratory. The wireless work in INL, or Idaho National Laboratory, has been always focused on the security and resiliency aspects of it. But 3 years back, we launched this Wireless Security Institute to bring special focus at the national level on to make 5G secure for use, specifically in the critical communications and using the national critical infrastructure. So, and of course, this needs a lot of collaboration at the national level with wireless security researchers in the universities, in the industry, in the government also. In my mind, the Wireless Security Institute really has 3 main pillars in the middle here. The research that we conduct ourselves, and we are fortunate to have the lab-directed research called LDRD, where we can start much ahead of time, looking down the road. And then that research normally again focused on the security of the advanced technologies and also the spectrum for it. And it has resulted in some inventions that are really being pursued widely by various government agencies, such as WSCOM, that's a waveform that can very efficiently and in a quiet way access spectrum intelligently. So that's what normally happens, that when we get started, then it widens with support from outside, mostly from the government agencies. And then the middle pillar is about testing and evaluation. So most of our wireless experimentation at the front end we conduct in our own laboratories over the air, but still indoor. We are lucky to have there's a unique wireless testbed facility in federal land, about 35 miles west of the town, where we operate our own commercial, cellular network all the way from 2G to up to now 5G with commercial equipment. So the location of the wireless testbed is very conducive to very low noise floor, RF floor, and that's really a good scenario to have for many of the experiments. Then in addition, we have the NTIA experimental station status that really we have a local spectrum management, and that really enables us to conduct experiments of our almost any frequencies. The last pillar really is the external collaboration, which really is important to do anything at national level. And starting from LDRD with 5G security, also we have very active academic collaborations and industry as well. And one of the main things that has been very helpful there is the workshops that we hold, mostly invited folks from across the country. And you can see that these are really workshops focusing on the relevant issues. And the last one was actually we went back to physical meeting in Salt Lake City on the focusing on aviation cybersecurity initiative. They actually, so that's focusing on the aviation wireless security. These are workshops, as I said, we really look at have a lot of good discussions, of course, followed by some good talks from across, where we can look at what are the security challenges, critical security challenges at the national level, what are being worked, what need more work, and how to engage with the government on this effort, because as you know, DoD and others are really playing a key role in the adoption of 5G in this country. So we have over 3 years, we have developed quite a very strong relationship with really very key research teams, and we welcome additional collaborations as we go forward. So just a minute to go through some of the key programs as I wrap up the WSI introduction, the main work we are focusing on for 5G security is really the DoD Operate Through program headed by Dr. Dan Massey. And you probably are familiar with some of the actually work being granted through NSF as well for the industry and academia. So academia in collaboration with industry. So there are 3 different configurations, as you know. That's the most difficult configuration to operate through is the untrusted. And then you have friendly operators. And then, of course, you have your own network, right? So we are focusing on the untrusted operator configuration. Then we've got the DOJ. This is the WSCOM that has really taken off with a lot of follow-on grants and funding. That's really proceeding very well. Started in LDRD first. Then I think I want to highlight 2 activities that are just started now, or getting to start probably in a really ramp up. The DOE CIO actually has started 5 key initiatives for nationwide initiative for across all the labs, DOE labs, and on advanced technologies. Secure use of it, of course, and we have lead on 2 of those. The first one was on the spectrum. DOE does own a lot of spectrum, and now that some of that has been shared and so forth, how to securely use it, do it securely. And the second one is use of 5G in the nuclear domain, right? The nuclear reactors and so forth, which has very strict regulatory requirements, and so it needs a very concerted effort to make it very clear that it is okay to use and proceed with the use of 5G. So very excited about that. And SF has, as you know, about the SciNERG activities. We've got 2 projects we collaborate with the ISI and USC, University of Southern California, and University of Utah. So that's really starting now. And as I said, LDRD, we've been focused on good collaborative research with universities on both the secure communication along with the dynamic spectrum sharing with spectrum sharing itself. So so I will now move into the 5G technology itself. This is a very simple diagram. I think you have seen many similar to that, but easy to start with very simple high-level view, right? Things get complicated pretty quickly. So what I'd like to do in this slide is just to have a review, I'm sure, or just to have a summary of the things that 5G brought in that changed completely from 4G, right? So, and then obviously then you can identify the changes and then what are the new attacks that can happen, attack surfaces that open up. So just bear with me. I think I'll take a couple of minutes on this, probably saying things you already know, but it helps to set up the talk here. The first, let's start with the devices. So that's moving from human operated smartphones that has been the dominant use till 4G to actually machine type communication, right? Which 5G makes it possible with all kinds of devices, connected cars, drones, all kinds of IoT devices, control systems, industrial control systems, connected health, all of those certainly is a big transformation of who uses the cellular connections. So now I think certainly attacks on a connected car or health device is a lot more consequential than a attack on a smartphone. However, the attacks initiated from the devices on the network on 5G, I think is the most serious attack surface that has come forward or has opened up at this point, because as you know, most of the IoT devices do not have the right security properties. And now that they'll be connected to a 5G cellular network, instead of, as I said, local Wi-Fi, I think you can imagine the change in the security picture here. Brief mention of the radio itself, right? In NR, a new radio that 5G brought along, really transformational in my view. That's in the device and the base station. The relevant, of course, you know about the capability to operate with variable OFDM carrier frequencies, right? Not just 30 kilohertz, but 60, 120, 245, 480. And that, when you go to a high frequency, you can see why, how the latency reduction is possible, along with other things like mini frame within the frame, right? So that's certainly transformational. The spectrum result is absolutely amazing. And that really enables use of the spectrum in a very flexible way. The spectrum itself, now that we'll certainly touch on it more, now that there is shared and unlicensed spectrum for 5G cellular, we certainly have the sharing business, right? It can be certainly attacked on that scheme that can stop anybody from sharing spectrum. So that's a large, very consequential attack. So that's different certainly for 5G. Going along to the next big change in the core network, as you know, the change to service-based architecture converted then all the network elements such as MME, signaling gateway, packet gateway in 4G to network functions, right? So AMF does MME now and so forth. But this really opened up the attack surface, because in theory, you can put in your connect these networks, implement them anywhere in the cloud, in theory. But anyways, even then, it's certainly a much wider attack surface, even if you implement them very in a local way. Now, I think if we look at along with that, then the technologies such as network function virtualization is Kubernetes, and of course SDN to deploy them and provision them. All of those are independent technologies, but they go along with 5G, right? So those are certainly attacks we have to be concerned about that can come across now in this big 5G play. Then going back here, the edge computing, right? So that has been really, really powerful, will be powerful and is powerful already to the seamless integration of the edge computing with 5G architecture. Again, that certainly goes with latency reduction as well. That those, I think, certainly are the quite a few very generalized attack surfaces, right? That we can think about now. Don't let me depress you, though. Next slide is that there has been a lot of good changes, right? Improvements. So as you know, the SA3 committee had done excellent work to make improvements, looking at what we had before up to 4Z. And here, so I'll use this one to briefly go touch upon the main improvements. And so I use a generalized architecture of where there is roaming. So this is the host network PLMN, and this is the home PLMN. This is the visiting one. So when we are in the same network, then they collapse, and this becomes the single network. So first of all, they're familiar with the starting to end sort of encryption of the IMSI or supine ADR interface, so that attacks like Stingray capturing IMSI is not possible if that's implemented correctly. Then we have certainly the user plane integrity, which can detect any alteration of data, which is pretty important for critical communication. That also is introduced for the first time in 5G. And then we have got when they introduce this service-based architecture, of course, they introduce security measures also, right? So all of the network functions now have to be authorized for you, the NRF. The network registration function itself is actually serves as the authorization with OAuth 2.0. And then the communication needs TLS between them, right? So all the network functions. So you'll notice that there's introduction of SEPP, which is the security edge protection proxy for when roaming is in place. And this really that's really safeguards the home network from attacks like the SS7 initiated attacks that anybody can query the home network about a user, if they can get to the user database and so forth. And so that should really help quite a bit, because along with that, securing this interface that not just anybody can come into the home network, that there is also additional, when there is IP access involved in between, there is additional security procedures based on JSON for encryption and alteration and things like that securely if they're not directly connected. If they're directly, of course, TLS takes care of that. If there is no IPX in between. But the next thing you'll notice is that there is this authentication that's happening in the home network. So that's brand new, right? In LTE, you go to a visiting network based on some, most probably record-based agreement or paper-based agreement. You get service in the visiting network. Just like when I visit my mother in India, I take my Verizon phone and it connects to the local network, right? It never gets verified back. And Verizon in 5G, any authentication always comes with the home network, right? So that's certainly a big improvement. So those are some of the key points. And where I'm going with is that next slide. Most often people will ask me, and you probably get asked the same question, some of you, is that what is the needed 5G security for critical communication, right? So for ordinary use, a lot of things are okay. But for really to say that, yeah, we can use 5G for communication that's critical, we really, I mean, looking at the improvements, I'd say that, yeah, I mean, there are quite a few good things here. User plain encryption, integrity protection. However, those are, secure, optional. So we to just make sure, I mean, it's not optional in the sense that vendors may provide it or not. I think the optional, in my understanding for 3GPP, is that since their domain is the whole world, they leave enough room for flexibility for various operators to use it the way, and there is overhead and so forth. So for the operators, these are defined as optional, right? They can they can turn it on or not, right? So so here we need them turned on. I mean, the actually user plain encryption, you probably know that it has been available in LTE also, but who uses it, I'm not sure. So, but for we do need them, and user integrity protection is certainly good. Now, I did not, you probably know about the 5G network slicing mechanism, right? So that's quite powerful. It's brand new. It's got a new network function. It's not just setting up an IP path. It's a lot more than that. By default, pretty much by default, there are 3 slices, right? One, so depending on what kind of, whether it is low latency, whether it is high band, high speed, or whether it is machine type, massive or large number of ID connections. You could pick one of those 3 things that everybody talks about in 5G, but there are a lot more slices that can be used. And one thing that can be powerful with slicing in combination with the secondary authentication using a authentication server like AAS, which can be procedure can be specific to a particular customer, like say a DoD, right? They work with Verizon, for example, to set this up so that for all their calls, their slice, secure slice, supported through that secure slice, there is not just the primary authentication, but multiple authentication. So examples could be for firefighters, for example, when they make a database lookup for critical information that's not accessible to anybody, there can be additional secondary authentication can kick in for those users. Another example would be these drones, right? Swarm of drones. If they want to form a swarm that's a local IoT group kind of thing, they can kick up this additional authentication, and not based on anymore on the SIM, but based on, say, the real ID that FAA requires now, or remote ID, sorry, that FAA requires for the drones. So very powerful mechanism. I think that can play a big part in securely configuring and providing service. Now configurations, right? So actually the configuration is a huge issue, right? So, I mean, for any cellular protocol, and 5G particularly, provisioning is a huge deal, meaning there are a lot of parameters, there are a lot of things that have to be set right, a lot of certificates that have to be managed, encryption scheme. I mean, it's not like flipping a switch, right? You can enable encryption, but then you can pick null encryption at this device, so goes to no encryption again. So things of that sort, you have to really configure and provision a large network, complicated network correctly to have all the security measures in place. Now, and other thing I would say is that there's certainly room for introducing security apps at the device itself and the application itself at the both ends, right? The application in the device and over the databases they access through 5G. Because you probably know that although I think the 3GPP has the structure, but there's not really anything that requires the UE to be, the user of the UE to be notified if some of the security properties are broken. So that's a big area that a lot of improvements can be made for particular implementations. But you can do all of these things, but certainly there'll be still, it's a complicated network, a lot of things going on. There'll be certainly attacks and problems, right? So now I think the AI/ML is really critical, right? To monitoring the network and concluding within reasonable time that it's an attack, and of course the subsequent steps. I think AI/ML, I think it's a no-brainer that something like that, the power of AI/ML has to be used. Right? So it's not anything that can be done manually or of that sort. So, and the zero-day attacks, right? I mean, the fascinating thing about AI/ML is it's completely continuously evolving. I'm not an expert on that. I know enough to be dangerous, maybe, or I can maybe a little better than that. But anyways, the bottom line is that zero-day attacks, I think I'm sure AI/ML is going to evolve or evolving already to even effectively identify zero-day attacks that has never happened before, right? And will certainly happen. So that's I think, talking about 5G security and challenges and the need, right, to continuously monitor and detect the any attacks going forward. So let's look at what's in the 3GPP framework, in what is already defined, and the NWDAF, right, Network Data Analytics. This actually is being defined well in, I think, starting release 17. I just looked up release 17 documents and find things that I really, that really looks promising. So this is part of the 3GPP architecture, core network architecture itself. Just like other network functions, NWDAF is there as well, communicating with the network function. I have a diagram here from the DS 23.228. That's release 17. Not so nice diagram, but then I pulled a better looking diagram from Capgemini's one of their documents. And by the way, release 17, really, there's nothing out in the field so far as I know. It's really release 16 going to be for a while. Release 17 is finalized, of course, sometime back last year. And equipment will be coming out, I think, it'll probably a year behind at least. So anyway, so this is just starting, right? So now, so the idea is that the analytics is inside the core network. So this is the framework there already. It can collect input data from the other network functions, like UDM, right? All the user flow, user data goes through it. AMF, all the control goes to it, session management and all of those things. So all of those can provide data to NWDEF, and then in turn, with the conclusions or detections and analytics, that gets back to the NFs, right? So very powerful NONM. So it's very powerful. Looking at the components, the DCCF is data collection coordinating function. So that's the data, how it is collected, coordinated, messaging framework, and the data repository function, right? The DRF right here that has the analytics and the collected data. Now the analytic logical functions are here in an LF that performs inference, right? And then derives analytics or including some attacks, we can see anomalous behaviors and so forth. And MTLF is the model training logical functions that with the ML and then exposes the services. So, and as I said, just like other network functions, the network, this NWDAF has also be authorized by the NRF and all other security provisions that are already there. So this is certainly a good framework. I just listed, it's very interesting, right? What are the analytics they've already defined as supported, right? So the first two, you can see that these are network slice and application specific information, not subscriber specific. Then you can see a lot of UE specific behavior, including UE related analytics, including abnormal behavior, right? So that's very important to be inside the core network itself. So, and then very interesting analytics group of, how a group of UEs you can track, or you can get analytics for a group of UEs that are in a particular area, and then how they are, how the quality goes over time. Dispersal analytics being where they are mostly doing their activities and so forth in locations. And even the performance on the WLAN connected with a UE, all of those really good stuff. So this is very promising, right? This framework within the core network. Now the other one is I want to talk about, bring your attention to, and I think some of you are probably looking at it carefully already, but again, I think the Open RAN, right? So there's a big push for it so that they can be plug and play in the radio equipment, open up the market. And the Orange standards, so far, and you probably heard about the Open 5G challenge that took place this year. All of that so far is really standardizing the interface between the DUs and RUs, right? And some of you probably know that even back in, I think, UMTS and going as far as back in UMTS, companies have been always using the remoting the RFs, the RUs, co-locating them with the antenna, and it has an optical CPRI connection. And the thing is that it has been proprietary, and now it is with ORAN architecture. This is really standardized so that you can plug and play different RU, DU, etc. But all of these, the black lines of the RU, DU, CU, all of that actually has been already defined in 3GPP, right? So I think the most promising change here is this the RNC intelligent controller RIC, right? So this near-time RIC, it's all in research right now. I don't think anybody really has any product yet, and it'll take a while for, even if some companies open up, and it'll play out as it plays out. But technologically, it is amazing. So the XApps, right? This is where I think we have to use the IML to really. So let me just give an example I'm thinking about. So this is the spectrum sharing, for example, right? It's sharing with DoD's military radar, right? So airborne radar. So there, the operator, they have to vacate that spectrum quite quickly, right? Milliseconds when that appears. So they can share it all they want when there is not there, but when they can use it all they want. But so something like that, the ability to move spectrum allocations very quickly, near real time, right? This is a really this is quite appropriate, right? So if it comes to, it comes to use by most of the vendors. Then of course the non-real time RIC is the more part of the OSS, service management orchestration framework, where you could look at load balancing, congestion, depending on congestion and so forth. All of the things that don't have to be near real time. So there's non-real time, and there are also the RFs called RFs. But all of this has to be fueled by machine learning, AI. And I think there's quite a bit of research, I think, already in progress on that. Here on this slide, I just want to give an example of use of AI/ML in INL. This is an LDRD. So it just shows that, yeah, I mean, it can be quite powerful. And here they actually have implemented in the FPGAs, shown that it's actually very performance. It's pretty good compared to big GPUs. So it's quite practical that using what we have already now, we can detect quite a few attacks. And here in this case, this is a paper in Globecom. I put it here if you want the more details. But bottom line is that these are all known attacks at this point on the core network, third-party attacks. So because mostly implementation problems, but that's all published already. But what is done here is that information extraction, things like querying the UDM to get subscriber information and so forth, and then network reconfiguration, really inserting a fake AMF and deleting a real AMF and things like that. And denial of service, where actually because of implementation problems, we could actually at one time, I think they fixed that now. You could even crash one of the apps if you send them some malformed packets. So all of this, I think there's about a dozen. It was collected in the lab, Iron Lab. This was earlier with V5GC and I think UE ran SIM. But they used autoencoder and variation also, and put it in a FPGA evaluation. And I think what is works pretty well. What is important is that they had this data is also available for use by others to experiment with, right? Detecting these attacks and similar ones with autoencoders and other techniques. So okay, so I think this probably, now I'm going to move into talking about spectrum, and let me make a quick check of our time. Okay, so please stop me, Dola and others, if and Suba, if I'm taking if I go beyond my time here. So this is spectrum. Looking at the spectrum. So that's other big change that I said earlier, referred to, along with the 5G protocol itself. The spectrum for use in 5G and going forward, of course, has seen a big change, right? You've seen FCC has allocated a lot of new spectrum, particularly in the millimeter wave, which was not used for cellular use before, starting with the licensed ones. I think it started in this country 39 gigahertz and 28 gigahertz. But overall, there is in the millimeter domain, there is about 5 gigahertz licensed spectrum. It includes some shared spectrum, right, at 37 gigahertz, and then unlicensed 7 gigahertz of new unlicensed spectrum. Now, if you go to the medium band, the sub 6 gigahertz, there is also plenty of new shared spectrum, and of course the unlicensed also, they opened up this 6 gigahertz, with 1200 megahertz band here, which is already being used by 6E, and I think it's also suitable to use by the 5G. So big change in spectrum, not only in this country, everywhere, right, in the whole world. There has been new allocations, making more 5G available, and of course 6G, I think, will probably jump to sub-terahertz, right? That's one of the trends that are coming up, although 6G standards are not written yet. So then I think here, in my mind, this is actually a transformational change that for the first time, a cellular network can operate without any license band, right? So that's the transformation really from LTE, we had the LLA, where you could combine, but you have to start with a slice of license band, right? So you probably have heard about that. The companies, operators have been utilizing unlicensed spectrum for 4G already, based, pulling in, adding that to the license band that they have, and they benefit quite a lot, right? So, but here for the first time, then we have you can set up a 5G network private, right? Because it's not using any of the license band, and utilize just like our Wi-Fi router at home, utilize unlicensed and shared band to set up a network, complete network. So now here, of course, that's in release 16 with two configurations. So the first configuration also is completely independent. Then you can certainly through internet and intranet, you can certainly talk to other public 5G subscribers and so forth, but that's only data flow, right? The second one is called hybrid, which is integrated with public network. And that's where it can really be part of a connected to a 5G network, public 5G network, which can also have control over this private network. So those are the two configurations. And the second one, it can be quite powerful if you think about say a warehouse or a factory facility where the trucks are moving out of their private network, and they can become part of Verizon or AT&T or T-Mobile, right? And that can be quite a powerful scenario also that that can play out. So, and a lot of happening here, lot more in Europe, I think, and then certainly US also, the manufacturing of Industry 4.0 can quite utilize this smart warehouse, factories, hospitals, airports, you name it, right? You can even nuclear plants, which we, as I mentioned before, that certainly will be moving in there. So very, very powerful enabling technology here that we have with the spectrum transformation for 5G and going forward. So so the main question is then, when you have to use spectrum band that you have to share with others, what is a really good way to do it? So if I look at this is an example, this diagram over to the right, and here assume that all of these four base stations belong to 4 different operators. They're all using the same band. And for this discussion, I'm assuming beam-based transmission, because I think that really, as you use beams with millimeter wave and even sub 6 gigahertz, that certainly makes it much more practical to share spectrum instead of having sector-based spectrum, where the overlaps can be quite significant. So far as the beams don't collide, right? And there can be partial collision and so forth, but I mean, this sharing can be very possible in a very good way, very, very practical way. Now the question is then, how do you decide, when to turn your beam on or not, right? So, and our approach is that, and I think there's a national approach also, really, we need more of this autonomous or distributed scheduling, where say we can run the same solution in all of the base stations, and this solution is based on data, sensor data is with their own EVs. But as you know, 3G for LTE, 5G has extensive UE measurement reporting mechanism. UE reports things to base station all the time about the spectrum. So utilizing that only, and not just taking decisions based on that, in a way that all of these base stations in a particular area without communicating to each other can make good decisions, so that overall throughput can be maximized, given the constraints that there has to be fair sharing, and that can be also tied up to limiting average power that can be used, right? So in addition to the maximum power that can be, each of them can use. So that's for that high-level collaboration with University of Utah. Professors Mingwu Ji and Sneha Kasera and their students, Chiang Chang and Samik. Really, we made, I think, really some headway into addressing this. And as I explained to you, I think it'll become clear what we have done so far, and there's a lot more to do, of course. So bottom line is that this is a scheme not like, as you know, the CBRS says, it's not really scaled, does not scale very well. Maybe it works in limited locations and so forth. And they're not centralized, right? So centralized, the security point of view, it's suddenly vulnerable central point of attack. And then having to rely on a different network, different sensing mechanism, right? That's really attack surface for falsification of sensing. And again, if you can disrupt that sharing mechanism, nobody will be able to use it, right? So that's a large scale attack. So this is what we looked at. Other thing I want to mention that we also looked at the worst, included the worst situation where two of the operators can have their antennas mounted, radios mounted on the same radio transmission mounted on the same tower, which is quite a common phenomenon, right? You drive around, you see some of the towers are quite busy. So co-located towers, base station towers are quite common. We have to address them. And of course, when they are co-located, the collision could be a lot more frequent, right? That's a challenging situation. So we certainly wanted to include that to see whether this will apply to practical situations as well. Now, so the basic idea is that, as I said, just to summarize here, the base stations, how do they choose to transmit to particular UEs based on their location and interaction in interference from other operators' UEs that can collide. So the thing is, when there's a lot of interference, of course, that's when you don't want to transmit much. You want to transmit when there is no interference, of course. The ideal, I think, where upper bound can be derived from this situation where nobody interferes with anybody else, right? So then everybody can use the spectrum all the time, and that'll be the upper bound, right, of performance. So in that case, when there is no interference, also you know that then the signal is quite strong, and that's when you don't have to power control. Also, you don't have to really spend much power if the signal is pretty clear. Now, you know, as signals gets SNR gets lower, then you have to do power control, maybe put out more power if you want to serve that UE and so forth. So the problem formulation, we went to the strength of the mathematics and physics and statistics to see what we can use here. The Lyapunov stochastic framework we used because we needed, so the virtual queues, right, were needed to really impose conditions, constraints like fair sharing and FRS power and so forth. And when we applied that, and there's also a guarantee of optimality and so forth with the Lyapunov approach. So it got decomposed into two problems, right? So the first one actually is a convex, so it can be solved. The second one is the one which is the main problem to solve, is the one of what power it chooses at the moment based on the sensing through the UV and what it needs to transmit. So that is the second problem, which is non-convex. And so, and the formulation is very well described in this IEEE Nixon paper, which focuses on the game-based distributed scheduling. So the second problem, we started with applying the non-cooperative game theory, right? And then we found the power of AIML, of Q learning, that improved it further. Now here, the main idea is that, again, the second problem is the direct problem to solve. How the base station decides what power to use or not transmit at all, maybe, right? Based on its history and so forth, and what it has to do. And then this first problem, we can pull that solution into the broader framework of Lyapunov because the first, it does have the cues, and then it produces the auxiliary variables and can be used as weights for the reward of the second problem. And I'll show you what it means. So now here is the typical example where we use the base co-located base stations along with also UEs to see, of course, they will expect different rates and so forth for BP1 power allocations, right? For cell-centered as opposed to cell edge. So all of that kind of we tried to build in here with the example of placements that are where the instantaneous placement of these UEs are, along with for each base station, each operator has 3 in this case, right? So now, so the payoff function for the base station itself is really, of course, the power, right? Depends on the power, because the payoff would be the data throughput, maximize the throughput, and that, of course, depends on the power that SINR, and this gives a measure of the data throughput for that UE for that base station. Now, of course, the penalty here is that the alpha and beta, the weights I talked about before, because if you use too much power, then again, you're creating more interference for others. And then, it's not really doing your fair share probably, because you don't want to be spending too much power, because that you want to be transmitting most of them when you have a better signal to interference ratio to take the fair share. So, and that's the individual, and of course the network is what we are interested in, not individuals. That is there are M base stations in this equation. So that's the summation of all of those. Now some details, very little details, but there's a lot more in the papers. The antenna model, of course, is with a beam width is theta, and then the MSR is the definition of the peak to the side lobe, main lobe to side lobe ratio. So the sharper the beams are, because that will make a big difference, right? I mean, that is the, really should be, that's the physics. When you have narrower beams, then there'll be less collisions, less interference, and it'll also be a lot better. Now, so the ratio, the signal to interference noise, right? This is the distance between the UE and the base station. Then we've got the channel characteristics here, H. And then, of course, all of these are from the other base stations and the noise, incremental noise. We use the Nakagami M distribution for the channel with small scale fading, and then I'm not talk about the game theory approach, as I refer to the paper that has good, very detailed summary along with the Lyapunov framework and the game theory. But what I'll say is that, yeah, the game theory, of course, did provide good results. I'll show you comparison, and there is proof of reaching Nash equilibrium in that game theory. So you do converse, do get results. But again, it is a very selfish scheme. It really does not understand it's not learning, right? So as you go along, so that's why we need learning, and we turn to Q learning, which basically without any model, it can learn over time. We take Q table. Now look at the axons are the ones. Axons is really the power allocation, right? What power the base station is choosing to transmit. It can be 0, not transmit at all. It can be some other power based on what its needs are and what the interference is, and which is S, right? The state is the interference from other base stations at that particular UE. So the epsilon greedy axon selection, I think there is randomly you can select sometimes with some exploration. And I think that's also necessary in a way to satisfy the conditions for convergence, right? Because each state should be visited for convergence. So that's kind of quite useful. And then the rule, of course, the learning rate and how much you discount the future axon with gamma. so that you can update. So this is a table then that you learn along with the environment and adjust. Very powerful in this case. For the axon and state, how we defined the axon, this selectable power transmission, right? So is of course quantized, and that the number of Q, right, number of power levels, we can quantize with that, and that of course, if you have more power levels to select from, you should have better performance, and we'll show that that's kind of quite intuitive. The state itself. Also the interference and the approach we had was that to the training phase, of course, you have to learn what kind of interference pattern is available is present in that situation. Then percentile based, right? You basically break it into, in this case, it's IQ, we call it. This is showing an example of how it can be broken into 10 different levels. So these are the states and these are the power levels to be selected. And so here, of course, to compare, I do provide the results from game theory are presented on the left side. And this was done with the bandwidth of 400 megahertz at 37 gigahertz. With a power maximum, we limited to 39 dBm, which is about 8 watt. So, here, there are three different colors. The colors are really the different antenna patterns. The red one stands for 10 pi by 6, 180 by 6. So the bigger than the middle one, which is 10 degrees, right? And 10 degrees, I think, is quite practical for millimeter wave beam widths. And this one is really very quite small. I don't think not practical. But the point is that the upper one that I mentioned are in the broken lines, which there is no interference. So every game agent or every base station can radiate all at once. That's the upper bound, right? So and as you can see, that as the beam sharpens, right, when it goes 10 degrees, the difference from the stable values are quite good actually. So that those are pretty good results for the experiments we ran or simulations we ran. But then if we go to Q learning, because particularly Q learning, I think it can learn over time the interference. For example, when there's collision and so forth, you can always learn of our time, and it does produce a lot better results. So obviously you see that when you have larger number of power levels to choose from, then the results are a little better, but both of them are far better than the game theory. And then here on this other one, we threw in some penalty, and this is without really considering the Japan of just looking at the game theory and Q learning, the second problem itself. Then if you throw in some penalty in the beta, then you can see that the game theory took a hit right away, but the Q learning adjusted over time, and the final results are pretty whatever it would be without any penalty. So I think it's 10 o'clock. Let me see. Oh, okay. The last one has the publications on this research, if you're interested to look at more details. And I think I'll stop at this time and take questions and so forth.
Thank you so much, Arup. This is a wonderful talk spanning a lot of different areas. Let's take a look at the questions over here, what we have. So the first question comes from Nate Rowe. Dr. Bhuyan, thanks for the talk. You mentioned ML research for detection of 5G zero-day intrusions, attacks, and abnormal behaviors. But sometimes once we detect, the damage is already done.
Right.
So the question, are you performing any ML research looking at vulnerabilities in existing 5G architectures to identify and correct for vulnerabilities before others exploit them?
Oh, very good question, of course. So yeah, in the ideal world, and the vulnerabilities should be corrected, right? Now the question is this, right? So actually it's quite a large job, and I'd say that vulnerability is really, okay, there are two kinds, right? One is the one that's in the probably is the protocol itself. That's something, there's something missing. And of course, this will take some time and effort to working with 3GPP and so forth. And you have seen some improvements from 4G to 5G for correction of, say, sending it clear on the air for IMG, right? So that kind of improvement is needed over time. Hopefully that happens at the algorithm, at the protocol level itself. But I think there is a different set of vulnerabilities, which is the implementation one, right? Which is anywhere in this, any software. And if you look at the NIST database and CISA database, it's pretty depressing, right? I mean, there are hundreds of, including in some of the open source systems, you can see in the list database, if you look at, there's for 5G open source, there's certainly some implementation problems. So yeah, completely. I mean, my take is that this is a huge job, and if you look at the DoD effort, what they're doing through, they've got all these grants from NSF to really come up with, survive those attacks, right? Or if they can't fix it, because sometimes they cannot really, they have to operate through environments they don't have control. So that's another environment there. So I would say overall, I mean, all of these things have to happen in parallel. Now zero-day attack, right? So, okay, actually one more thing. Vulnerabilities are always going to be there in hundreds and thousands. Now, the way we have to approach this is that which are the exploitable ones, right? In a real 5G domain experiment, in when it is in serving hundreds and thousands of users, are there really things that any of these vulnerabilities then can be exploited, right? And what are the impact and how is likelihood and all of those things. So I think so, the ones that are highly likely and has large impact, of course, have to be the focus first. Now, 0 days by definition is not really known before. If you knew the vulnerability is not 0 day anymore. So that's my understanding. I think other people, others can look at it different way, but that's, I mean, I think we need the power of AI, right? I mean, the example I gave, the autoencoder, it was not trained for those vulnerabilities. It was trained just for normal traffic, but it was able to detect those concrete attacks because, it knows what is the normal behavior, right? So detection will be a big deal because not everything will get fixed, and even things that are not known will come up. So thank you, but very excellent question. No simple answer.
So the next question comes from Hongwei Zhang. On the education side, are there any community or open resources, for example, labs, learning modules, test beds focusing on 5G or next G security?
Wow, really good question. And I think over time, I hope it develops. I think we are doing some work now, and hopefully we can also take part in that effort to have more available for other researchers. I think the data set, that's why I mentioned, I think those things are important, right? You don't have to go in the lab that we already had to collect the data set. You have that available now publicly. And if you have any difficulty getting to it, certainly can get our principal researchers on that in touch with you and so forth. So we'll help where we can, but yeah, I mean, it's work in progress and very beginning, I would say.
Sure. And the next question again is any pointers on field measurement studies or data on security vulnerabilities, effectiveness of the state-of-the-art countermeasures, and open challenges from real-world deployments?
Unfortunately not, right? The real world deployment is just starting now. And everything that is happening, and I'm glad that actually in our lab, we have got some real data, right? Because I don't know anywhere I can go and get 5G security attack data and what is effective or not. And we are still learning some of the things, right? What could be attacked, what cannot be, my focus right now is really using the data we have in our hand right now, because we are fortunate enough to have that in our lab, to really understand how it works and whether that's, what is it's behaving as it is designed. And if it is behaving as designed, it is really effective, right? That it really solved the problem and so forth. So yeah, so I think we have to all learn together at this point. A lot of work there.
So the next question comes from Moinul Hussain. What are your views on implementing 5G for critical military applications, such as contested radio environments? In other words, how does 5G need to evolve for resiliency against attack scenarios that are not considered for commercial 5G networks?
Yeah, no, excellent question, right? So the resilience, I think, is the other side of the security, right? I think the resilience, I look at it, is that once attacked, how they can recover, right, safely. Whereas the security measure is there to actually prevent those attacks. But so the only thing I can say, and I'm learning too, I would say that, again, I go back to a couple of things in that slide I saw. One thing is we have to use everything that's available through the standards, even though it's optional or takes overhead, right? And we have to figure out how to minimize the overhead to make it practical. The second thing is, use again all the 3GPP in structure, the architecture, and def and other things to really detect them if things are happening. And the third thing is to have, in addition to the 3GPP security procedures, really have additional security measures. And I think I always think about the device itself, because a lot of times the device you can own, right? You can go to a operator and get their SIM card or eSIM to use your device, but your device, you can have things for resilience, security, and resiliency also, which would be a lot more suitable for use in such a network. Even though the network is not secure and resilient 100%, even good networks, this certainly cannot, there will be always attacks. So I hope that answers your question to some extent.
The next question comes from Marco Hernandez. Regarding 5G security, how does 5G handle security for EV outside of the cellular network coverage, but still associated with 5G specifications? For instance, in vehicle-to-vehicle configurations out of coverage of the cellular network.
Yeah, okay. Yeah, no, that's a good question. Let me see. Oh, yeah. So vehicle to vehicle, you're absolutely right. And actually that's I think you're referring to the side link, which is D2D, device to device. And V2V is one application, but remember that V2V can still happen without D2D, right? But when you have D2D, then even the vehicles are out of coverage, that's what you mentioned, that they can still converse without going to the network, they can talk among themselves. Very, very powerful capability, the side link, right? Now, I was trying to look at the security of that, and then I figured, I found out that the device-to-device actually is a for 5G. They have it in release 17. So we'll get to it pretty soon. See what are the specific security procedures that can be applied, because and that I think is going to be a huge area. B2B itself, working with DoD, that's there actually. When we ask them about use cases of importance, they always talk about V2V, right? And the Department of Transportation is also working a lot on that. So I think that's a really good use case. Device to device itself not only will apply to B2B, but swarms and other things, groups of medical devices, all of that, and the side link capability when they are not even, they are registered to the 5G network, but they don't have to use that. Even if they get out of coverage, they can use one of them as relays for the one coverage, or completely stay off the coverage and then continue the communication among themselves. So great topic.
Sure. I don't see any more questions in the chat, but if any one of you have any questions, please feel free to unmute yourself and ask the questions, because we have a very small group right now. Most of the people have dropped off. Suba, any questions?
Not any specific questions, but I know you did mention that you have some data sets. I'm trying to understand what kind of data sets you have. And you said you did mention that you have it publicly available. So if you can give a little bit more idea about that.
Sure, sure. So this is the data set that the LDRD actually used. And that has about 12 attacks, I think. So there are three different areas, and these are published attacks, exploiting vulnerabilities that are well known already. But for example, the first one was the class was messing with the core network, right, from outside. These are all third-party attacks. So specifically, this one was querying the database for users to extract information. Right? Now, if it was installed properly, if it was provisioned properly, that would not happen, right? Because so there's either insider information or something, because you should not be able to query with the TLS and OAuth. So that's certainly fault in the commissioning of the equipment, but that can happen, right? That can easily happen. So that's one example. The second example was where they actually inserted a fake EMF into the network, right? So again, it does not set up properly in the fully correctly, securely installed core network. That should not happen unless you have access to the network, right? So once you can do that, you can actually then direct some traffic also. So instead of directing to the destination, then you can redirect to yourself, for example, right, to your own server. So that's another attack out of the dozen. And the third one was actually, this was certainly coding problem and the core network open source, that you could actually, if you send a malformed packet, one of the network functions will crash, so taking down the whole network, right? So there are, I think, 12 different attack scenarios. The paper describes them all, but these are all third-party attacks on the operator, and all can be preventable with right security. But still, I think there's something to experiment.
And I assume that the links for the data set is available in that paper, right?
Yes, yes. Yeah. And they have stripped down the IP addresses and things like that, so that those are not, you are seeing, all you're seeing is the pure data, right? Instead of a lot of additional information, which sometimes you can derive information from those also. So.
True.
I have one quick question, and I think my question is, we can have attacks either in physical layer or in higher layers. When we are looking at packets and all of these, the timing of the packets, malformed packets, as you mentioned, so these have to look at different set of themes or a different set of parameters. On the other hand, if you are looking at physical layer signals, for example, if someone is transmitting a radar signal, which is not DoD signal, or something that you would assume that it's a primary transmitting, but actually it's not. So all of these are different kinds of vulnerabilities. And
yes,
what do you think that how we can tackle different sets of vulnerabilities? Because one is with signals, the other one is on bits.
Yeah, right. I mean, I would say that, signals, yeah, absolutely right. But once you can collect them, eventually it'll become IQ signals, right? So right. I think then the focus should be looking at the IQ signals itself to see what is going on, right? So, so in this case, it's different kind of packets, but certainly as important, right? So I would say that it's a different domain, right? The RF domain. Then, as I said, there's certainly it's a big, it's an attack surface, and certainly being able to observe that and derive conclusions and subsequently maybe act on them, those are very important area of research also.
So you hope that there will be like two sets of or multiple sets of these machine learning tools. Each one of them can look at different sets of attacks.
Absolutely.
Okay.
I mean, that's what scares me, right? I mean, there's so many different things to look at. I mean, these are large areas of things, and yeah,
Sure.
absolutely.
Sure. Okay, I don't see any more questions at this point. So let's thank the speaker. And it was really nice to see all the questions coming up and all the info that we learned about INL and the security work that is going on there.
It's my
Thanks,
pleasure. Thank you all.
Thanks,
Thank
Arup.
you.
Bye.
Have a good day.
Thanks, everybody, and bye. See you in the next talk.